sharp. So I am very happy that we'll have now Gergo Orban, who from Budapest, who will continue kind of telling us about perception and adaptation. So Gergo is a good man since he's a physicist by training. He did a PhD in physics, and then he did a couple postdocs then in computational neuroscience at Brandeis at the Voland Center, and then in Cambridge, England, where he worked with both theorists and experimentalists. And his work, he has done a number of very nice things, mostly kind of applying machine learning approaches to problems in both computational neuroscience and cognitive science on perception, adaptation, inference, as you'll see. So thanks a lot.
Lovely. Thanks for the interaction. And it's just exciting to be part of a multi-continent presentation. So hello everyone in Beijing. I don't want to leave the meeting. I have something here which tries to get me. No, I got it. Okay. So right. Okay. So back in Budapest, I'm heading the Computation Systems Neuroscience Lab, which might suggest that I'm interested in neural stuff only. In fact, I'm equally excited about behavior, and I see a great potential in understanding behavior and characterizing behavior in as much detail as possible, and learn of the brain from the behavioral aspect of the data. However, today I will speak mostly about neurons, neural activities, and how the brain works solely based on the neural aspect. So I will sort of capitalize on Manish's talk. I will both step back from how Manish approached the problem, and we'll use his presentation as a springboard to delve into topics that I thought I will never have time to speak about. But since Manish was kind enough to cover some stuff, I will be able to do that as well. So that's cool. Okay, let's try something else. Okay, how is it now? Okay, I see what's happening. Okay, lovely. No echo, no more echo. Cool. Pretty much all of us are interested in modeling the brain, and computational neuroscience is concerned with modeling the brain. Still, one of the rather confusing or frustrating aspect of modeling is that it is hard. First one needs to specify what we mean by coming up with a model. One might consider model as simply a minimalistic model that tries to account for some phenomena that we see in neural activities. Let's call these mechanistic models. Or one might consider other models which, when we record tons of neurons, try to use some techniques, some machine learning techniques, just as the sort of techniques that I'm using for making the data in a form which is more interpretable. Let's call these descriptive models. And the approach that I will take here is a slightly different one. It's related to the one that Manish presented, or very much related to what Manish presented. We try to model based on what sort of things it encounters, how it interacts with the world. So the idea here is that the brain is embedded in an environment, and through perception, we do inferences about the environment, and then just as Manish also pointed out, the whole goal of this thing is making some sort of actions. If we just try to break this up a little bit and focus on how perception will be useful for us, or the sort of mechanisms that are involved in perception, then what we see is that first we need to make inferences on our current observation. These inferences are not standing alone, but these inferences are also based on our past observations. So we collected data earlier, and somehow we integrated our previous experiences with our current observations. And this way, we somehow, from the past observations, we come up with some learned regularities of the world. And so one of the most exciting aspects of the brain is that it is actually doing some sort of an adaptation towards the environment. And one can be excited by adaptation solely by the fact that, well, we have a sort of a dynamical system that is changing all the time. But I will take a different approach, which is this. Since the brain has adapted to the environment, we can take this environment as sort of the driving force for understanding how the brain works, because it has adapted to the environment itself. So after all, what I will end up with is this sort of model. So what I try to do is that I want to understand the brain through what sort of internal models it comes up with about the environment. So I want to characterize these internal models through natural statistics. So just one by one, this is the sort of code book that I will go through. So the adaptation being the main contributor to shaping the brain, and then this natural statistics is the thing that was driving. So then we can identify the relevant computational principles that might be good enough to make efficient adaptation. Then we will use computer vision models, and this is a crucial part. Computer vision models or machine learning models that are somehow good enough to deal with natural like statistics. And from these computer vision models, we try to predict neural responses. So one way to approach is this. There's a huge industry built on training models based on for instance, the ImageNet database, and then these models work on some sort of a predefined task like classification, which is the sort of the most obvious one. You want to tell apart cats from dogs, and one might say that, okay, so this is a particular task, but the categorization itself, it might be an important one. Still, I think that a great justification for this approach is this is sort of a very constrained form of a Turing test, whereby if you are able to train an artificial neural network that is performing as well as humans, then you can check whether this model, this artificial neural network, produces similar patterns in neural activity that biological agents do. So the evolution of deep discriminative models was such that starting from the early 2010s, the classification performance on this ImageNet database, these are hundreds of thousands of different categories that the neural network was supposed to efficiently distinguish. So the error rate that we measure on this data set was drastically dropping, which was a nice thing. And at that point, Andrej Karpathy was kind enough to set a human benchmark for classification. So he himself did this task of trying to classify these images. And the red line is actually him. So this is how we, as represented by Andrej Karpathy, perform this task. So this then will be taken as a sort of the constrained Turing test. Our beautiful image model, AlexNet or whatever that was, is sort of performing similarly to humans. So then the question is, the question, the model is built up similar to the human ventral stream, which is a hierarchical structure. Processing stages are built on top of each other. So if its performance is comparable to the human performance, then will the building blocks behave similarly than humans do? So here I will just scroll through a bunch of results on this topic, how well these models perform. The easiest form, yeah. So what they did was that they used a bunch of images to fit. So first, let's go back to this point here. So if you see my cursor here, so they have a small constraint that they relate the activity of their artificial neurons to neural activity through a simple linear mapping. So it's not a one-to-one mapping between artificial neuron and the neuron, but sort of a mixing of ANN responses will result in a response in a real neuron. Then if we train, so we want to find this mapping A for a bunch of images, and then we can predict the neural response on images that were not used for training this particular matrix A. Okay, and so this is what they see. The performance of the model of their mapper A is solely tested on training data. And so here on the horizontal lines you see 1,600 test images, and the responses of the neurons are plotted in black, and the predicted response plotted with red. And the match is remarkable.
Sorry, the x-axis is what?
The x-axis is a number of 1,600 images, and the y-axis is the response of the particle neuron to that image. So these are 1,600 mean firing rates for these 1,600 images. Make sense?
Why is there strong autocorrelation in the?
Sorry?
Why is there strong autocorrelation at the time in the series if the horizontal axis is image?
I guess that this relates to the object category because they are recording from inferotemporal cortex, which is sort of sensitive to object categories, and these shadings corresponds to different categories of the images. And more than that, it's interesting that if they try to correlate which of the individual layers in the deep neural network predict best the different brain areas activity, and they find that those that are earlier in the processing hierarchy predict better the ANN neurons earlier in the processing hierarchy, which is a cool thing. So those which are in V4 neuron activity can be predicted by earlier layers in this hierarchical convolutional neural network, and IT activity can be better predicted by later layers. Okay. So this is a beautiful baseline. And then one can go further, like you can design images such that you want to have images that elicit the most intense activity from a neuron. So you can imagine that you start up from an image and you do some gradient ascent on what sort of activity you expect from the neuron when you make jitters in the stimulus. And here's one particular stimulus that was optimized to drive the artificial neural network the best. And then the prediction is that if this is true, then it should be true that if it is a good model of the brain, then it should also be true that this will drive strongly the biological neuron as well. Okay, and this is also what we find. What is found. Naturalistic images are shown in blue, and these engineered images are shown in red. So this is the predicted and the measured firing rates. And what's the most striking thing is that these engineered stimuli drive very strongly these neurons.
So I have two questions. First of all, what's the loss that the network is trained on? And secondly, I didn't understand, you do this ascent for one neuron or for a class of neurons?
No, this is for one particle neuron. So you have R equals A times Y, and you optimize it for R being the highest. The other thing that you might refer to is when you want to train it such that the stimulus is most selective to the particle neuron.
Okay, but then when I want to find the correspondence in the real brain,
yeah,
I have to look and find that neuron.
No, so on natural images, you optimize A, the mapping from the artificial neurons to the real neuron, right? And then the optimization, then you optimize an image X such that R becomes maximal. Okay.
Oh, I see. I understand. Okay, fine, I understand.
Okay. And in the first sort of exercise, they do it such that they don't care about the activity of other neurons, which is signified by the fact that this distribution is wide. So neuron 2 can also produce high activity. And another exercise is when you want to be selective for that neuron, the stimulus being selective for that neuron, and they show that they can produce these very selective images as well. So I think that this is pretty cool because originally these images were just trained for classification, or these models were trained for classification. And then you can go down the road and push this to pretty effectively predict neural behavior. Now, this is one more thing that is even cooler. It will actually show the limitations of this approach, but still it's very cool. So adversarial attacks are known that are sort of harmful for these deep neural networks, which is that you have an image and you can engineer another image, which is you just add noise which you cannot really perceive. Still, the classification of the classification performance of the neural network will be rather full, because when you ask what this is, it will say that it is an ostrich. Then you will have another one. Again, you engineer it, and you will get an answer that it is an ostrich, and you might have some other ostriches as well. So it's a headache for computer vision people. Then Jim DiCarlo and his colleagues took it to another level. So if there are these adversarial samples that challenge the deep discriminating model, then is the brain also susceptible to these adversarial attacks? So again, in the artificial neural networks, they design stimuli which are challenging for classification, and then you have control images which the neural network can classify pretty well. And what you see is this: the control images. The performance of the neural network is similar to the performance of the monkey. I will get back to what monkey performance is. So the performance of the monkey is measured as how well you can decode the object trajectory from the neural activity. Okay, so the monkey does not have to respond. Categorize anything. You just want to use the neural activity to do the classification from inferotemporal cortex. And for challenge images, what you see is that the performance of the monkey is much better than the performance of the deep neural network, which gives pride that we are not that easily fooled than the neural network. What's interesting though is this. So they hopefully, yeah. So they did this. They measured the decoding performance, decoding these categories from neural activity in different time windows from stimulus onset. So you might have a sliding window, and you measure when you can do the decoding pretty well. And so when you can so if you have now behavioral task where the animal needs to do categorization of several categories, not hundreds or thousands, but several categories, then you can measure what the behavioral accuracy of the animal is, and you can use it as a baseline for decoding from neural activity. And so this way, you can measure at what time point you get to the performance of the behavior with your measurement. Obviously, your measurement is sort of limited by the number of neurons that you record. So it's not an objective measure. We just want to use some sort of a sensible benchmark. Okay. So this is called the object solution time. Hopefully you will see it if I move this down. Yeah. And what's fun is that it seems that the object solution time is different for those images that are belonging to the control images than those that are belonging to the challenge images. So this object solution time is longer than for the challenge images than the control images, which tells us that it's also true for the animal that it is slightly more challenging to this task, and they conclude that some sort of and I agree with them that the feed-forward sort of processing that is implied by deep neural networks is not sufficient to account for the computations that might be there in the parent temporal cortex or the ventral stream. Yeah.
So there was a question on the chat that asked, what are the black dots in that graph?
The black dots in this graph, which I assume are these, those are the sort of the intermediate responses. So so those images which are not necessarily classified as challenging or control images. Yeah, some additional parts. So the bottom line is this. So we had these deep discrete models. Yeah.
Is there before the slide before? Is there any way to see actually what is the error made? Like, I mean, the decoding performance is up.
Yeah.
But like now I don't know exactly. You have that you have these different categories, and then you have the probability that the image belongs to different categories.
Yeah.
Is there a way to measure actually how it rises up? Like the best category starts to increase, or like the best category before it's some completely other image, then the winning category after a certain point starts.
Yeah, so you're referring to assessing the actual multinomial distribution of the classifier and whether there are any patterns. I'm not completely aware of this sort of analysis in the data. So I guess that this exercise that we did is pretty cool in the sense that these models were not meant to be solely a model for the brain. These were meant to be good models for classification. And so what we want to do at this point is identify the sort of computational principles underlying this model. And it's really just a nutshell summarization that the computation goal here is classification. The architecture is a hierarchical, just like the brain. It is feed forward, not like the brain. And the learning itself is something that we call task specific. So here, the adaptation that I was earlier referring to is something that is rather specific because this thing was trained to perform well in classification, and obviously one expects that the sort of thing that it can perform and the representation it builds up will be task specific as well. And I think that one of the bottom lines that I want to draw here is that we know that this feed-forward architecture is not really the thing that is there in the brain, and it seems that these adversarial samples highlight something about the inability or limitation of this feed-forward architecture to perform well in even in the classification task itself. So what I want to point out here is that one of the main thing here was that training that was there was a supervised training, which means this. So when we have an image X and a label Y, this deep neural network learns pretty much just a mapping between the labels Y and the stimuli X. As one of the so the F itself is a highly nonlinear function. This is the peak of deep neural architectures. But as the question pointed out, what you actually learn more formally is this conditional distribution. What is the probability of having this or that category given an observation X, right? And then the training objective is some sort of distance between this distribution and the ground truth distribution of the labels Y. So this has two consequences. This training objective asks for a lot. It means that you want to have for each and every single image a label that you can match. And the other thing which I alluded to earlier is that what we get is a task-specific representation. Now, what we can do now, so then if it was a sort of a supervised setting, then let's start out and say that, okay, we want to have an unsupervised model, and we want to learn about adaptation in an unsupervised model, adaptation to natural scenes in an unsupervised model. So here in an unsupervised setting, the goal is not matching the image labels with the predicted labels. Rather, the goal of unsupervised learning can be phrased as learning the distribution of images, right? So if we have a distribution of images P of X, then we want to have some sort of parametric form that approximate as well as possible this P of X. Well, it's on one hand you can consider it as an ambitious project to derive brain properties from this very simple objective. On the other hand, yeah, it can be underwhelming as well because, well, it does not sound really exciting. So we want to find these parameters, and then just to have some sort of formal definition of what we want to have is done through a measure called the Kullback-Leibler divergence. The Kullback-Leibler divergence measures sort of the distance between two distributions, such as the P and Q, and this measure, also called the relative entropy, has this property that it is always greater than 0, and it is 0 only when the P equals Q. Okay, so then this can be formulated as a training objective for an unsupervised learning. You want to minimize the Kullback-Leibler divergence between the two distributions. In our case, if we have a bunch of images, so one note here is that, so if we have a large set of images coming from P of X, like here, then we want to integrate over all possible images, and then we obtain this sort of distance measure. Yes?
Oh, well, shouldn't the equation for the KL divergence be P times log Q minus log P? There's something funny with the bracketing and the P there. P times log of Q minus log of P.
You just forgot to bracket after
Yeah, sorry.
Q of X.
Yeah, sorry for that.
There's a missing bracket after.
There's a missing bracket, which I can emulate here. Sorry,
Yes.
here is a, sorry for that.
So maybe a question. So P of X is the empirical distribution
Correct.
of the images you use
Yeah.
in your. So maybe can you define Q of X?
The Q of X is an approximate distribution that wants to somehow. I will go into that. So it's the Q of X is meant to be the same as P of X. The P of X is not a parametric thing. It's something that it's an empirical distribution, and somehow you want to have some funky form of this Q that can be parameterized by theta, such that this distance can be minimized. And in practice, we have a bunch of images, xt's, and instead of this full integral that we have here, we just do a Monte Carlo integral, which is pretty much just a sum over available data. Okay, and one more sort of relief is that the second term does not depend on theta. So this way, what we are actually doing is that we are maximizing the so-called model log likelihood, meaning that on every single data point that we have in our data set, we calculate the probability of the parametric distribution, and we try to find the parameters that maximizes this. Okay. Okay, so here I just want to state this that in supervised learning, the cost function is measuring the distance between the predicted labels and the real labels, and here we are matching. We are trying to match the distribution of the parametric model distribution and the empirical distribution.
There's a question regarding the formula in the last slide.
Yeah.
Regarding, I think, the multiplication. So the question is, why is in the formula? So I guess the formula what implies the P of X loss.
Okay, so
by N.
do you think that?
You can write.
Maybe.
But
Yeah, but I need to.
Yeah, you have to construct them.
So maybe I will try to do it in just in Word. So what we are doing here is that the Monte Carlo integral. So normally you would go through all possible values of x, and for each and every single value of x, you calculate the probability of x, and this will be a weighting factor for the formula that's here in the bracket. Here in the bracket, this whole thing. Sorry, let's say this. So here in the bracket, so the probability will be a weighting factor. And instead, what you can do, instead of going through all the possible values of x, you can substitute this integral or approximate this integral by getting samples from the empirical distribution and do an averaging over the empirical distribution. Okay, it's just like in basic probability theory, you can, if you have samples from a probability distribution, then the expectation with respect to the probability distribution can be performed by sampling from this distribution.
There's another question.
Yeah.
So just on the last question, I think that the point the person was raising was that for the sum to match the integral to correspond to the weight term dx, you could just divide by n sides of the data set.
Yeah, correct.
There's
Yes.
another question. Can you define the loss function in supervised learning with respect to these probability statistics?
Yeah, so in sort of hand-wavy way, the loss function in the case of the supervised learning was sort of a cross entropy between the cross entropy between the labels and the real labels and the predicate conditional distribution. In that case, it was P of I given X, and you had the real labels, and the cross entropy between these values was the loss function. So in terms of formulation, it has very strong similarities. What you are actually doing is quite different, because in one case you are operating in the space of pixels. The pixel distribution should be matched. In the other case, it is the label distribution that needs to be matched. So yeah, it sounds cool that I defined adaptation, but it's hard to understand where the neurons are and how it relates to any sort of features that we might have in the environment. So the answer lies here. It's actually buried in another additional layer. The way we actually can effectively represent the probability distribution, and I hope that in the next slides I will make it more sort of palatable how we go around this. So the question was from Rava. So what sort of how would I come up with this Q? One could actually measure like the statistics of individual pixels, right? How intensely pixel 1 generally activates, pixel 2, and so on. So this is something called just marginal statistics. It treats pixels, individual pixels, as independent, but you can characterize this distribution then with if the number of pixels is n, then with 2 times n parameters can characterize this simple distribution. It would be a parametric one. Or the second order statistics would be the correlations between a pair of pixels. Then you will have, for the covariance, you would have 3 parameters, and for the mean 2 parameters. With 5 parameters, you would be able to characterize the distribution of 2 pixels. If you scale it up, it's obviously insane, because if you have large images, then you will obviously have a larger number of parameters. But the problem is more this: if you want to have even more intricate statistics, if you want to learn even more intricate statistics like third order statistics, then the number of parameters that you need to acquire to need to learn is scaling exponentially. So one way to do this is this. This is a motivation. So we believe that our observations are a result of some underlying causes. So observation X is something like coming from the fact that in the environment there are some features like objects, and this will be mapped somehow onto our observations, and we assume that there is some sort of a noise. So the linear case is simple. It is something that Manish also covered, so I will be able to go through that quickly. So there, the mapping between x and y is simply linear. So we assume that like these transparency slides are there, which feature the different features of the environment, like house and sun and cloud and so on. And these are overlaid, and this is how our images are come about. Okay, so in that case, the x is just this simple linear mapping, and if we formulate it as a probability distribution, then this is the x is actually a y here, I guess. So the mean of the distribution is a times y, and the variance will be determined by the sort of noise that we have here. Okay, so then we have this distribution that describes how we believe our observations were made. So this is in 1D, and in a multi-pixel world, there is not a single pixel. Then again, we just have a normal distribution. Okay, so then we are pretty cool. We are in a pretty cool state. So this structure in whatever seen in X as a structure, it is traced back to the structure in Y. So these are the latent features. So whenever I see correlations between the pixels of the environment, these pixels correlations come because there are sun and cloud and students and stuff like that in the outside world. So this is called the generative model of the environment, and then the image statistics has a pretty simple relationship to the distribution that we defined at the left-hand side of the slide. So we have this part, the Q of X given Y, and we need to according to the principles of probability theory, we need to marginalize over the possible values of Y. We will go into the details of what this Q of Y is, but right now the bottom line is this: once we sort of formulate how we think the axes are generated, we can come to a formulation of this approximate distribution Q of X.
I think for people who are kind of familiar with this, it's kind of feels natural, but for people who are not familiar, maybe can you say a bit, but why would you even have noise, and why would this noise be normal?
Okay, so the normal noise, the noise that we have here is in general terminology, it's called the observation noise. The easiest way to understand the meaning of the noise is that everything that we cannot account or do not want to account for with our model. So whether it's the easiest reference is noise in our senses, in our sensors. Like in a CCD camera, you have noise. In our receptors, we have noise. But it's actually a more fundamental thing, something that we are unable to account for, ambiguities in the environment, or some sort of mappings that are not invertible, whatever these mathematical processes. So the noise itself is sort of a vanilla term for all the things that we cannot or do not want to account for. And it helps. So the reason why we have it there is that it actually helps learning. If we are aware of the fact that we cannot account for everything, then it will be able. Then it will make us more effective in training our models. Okay, so then what we have here is that in this generative modeling approach, why? Yes.
Just a follow-up question from Robert. So I guess that this Y is kind of like the hidden causes that Manish talked before this.
Correct.
So
Correct.
then the notion of noise can be extended to invariances. So it doesn't need to be only measurement noise. It can be like, like a translation.
Absolutely.
But that means that the noise model that you need to introduce will be much complex with correlations. I mean, when you shift something in particular direction. So this is a horrible type of noise to model in pixel space. So,
yeah, so
what are these eyes? Why? Sorry, you don't want to.
Yeah, so the thing is this. So if you have a complex image set and you have a simple model, then obviously there will be tons of residual structure that you cannot account for. For instance, if you have just a linear model, then it's obvious that you will not be able to learn all the complex features of the bird that are characterized by the invariances that you refer to, like in the inferotemporal cortex. Those neurons that are sensitive to a particular object, they are insensitive to variations in the pose, in the lighting, scale of that object. And it is the question of this F that defines what sort of representation we might have. So if you have a very complex nonlinear mapping, then it will be able to account for these invariances, and then your neurons will show these invariances.
But don't you need to introduce this noise inside propagating this noise?
No, if you have a model that is capable.
This Gaussian model is not a good model for interesting invariances, right?
So the Gaussian part in this model is only referring to the residual noise that you cannot account.
That's not interesting.
That's not interesting.
Noise.
You want to have a model that can explain the most variance in your data.
Right. How do you do that?
And the way you do that is that you want to learn more and more complex models, more like a hierarchy of these is Ys. On the first hierarchy, you have just some linear relationship and then more non-linear. And then these hierarchical layers, will suck up more and more of this structure that is in the data. Okay, I started off with the linear one because it's easy to understand, and later on we will go for nonlinear ones, which where we just need to have guarantees that it can learn some sort of structured models.
Yeah, is it a good time to take
Yes,
10 minutes?
I was thinking of that.
Okay, so let's take a 10-minute break and gather at 5.
Values of a pair of Ys. So it tells us that Ys are independent, and also so because it is invariant to rotations, the Ys are considered to be independent. And this is something that Mani spoke about. You can have an alternate prior where. And this can be sort of an assumption. If Ys correspond to neural activations, then you might want to have a representation which is such that neurons tend to be close to zero with their activations. So the activation, the distribution, or assumption about Ys is such that the neurons are mostly inactive and sometimes they speak, but rarely. And this can be formalized in a distribution which is called a sparse distribution. Yes?
Just curious why it makes sense to interpret firing rate distribution like that as funnily shaped prior rather than a funnily shaped method of decoding the neuron firing rates to turn them into hypotheses about the.
So maybe I don't know what is the exact answer to the question, because I try to understand the question. The neural activities are affected by the prior, but in fact the neural activities correspond to the posterior. Okay, and the prior only sort of quantifies this contribution of the prior, how what sort of representation we want to learn about the environment. We don't care how much energy we spend on representing any particular image, or alternatively whether we care about it and we want to have a representation where neurons are mostly silent. But again, the actual thing that neurons do is so the neural activations are characterized by the posterior itself, which is affected by the prior, not exactly. But I'm sure that I did not answer the exact question you asked.
So why is that the neuron firing rates, are they?
Yes. Yeah, and so in order to be easier to digest, I would say that the Y's can be the membrane potentials, because the firing rates are positive and Y's can be negative as well. So let's just consider this at this point that Y's corresponding to membrane potentials. And then it is not that funky, this shape of the prior, but this is the so-called Laplace prior. Sorry. So this is the Laplace prior, which again is a sparse, not that sparse as the one that is shown here. Yes.
Is there any way we can find which type of prior we should use for certain specific exams?
That's a lovely question. So in 3 slides, I will get to that. So your question concerns the validation of the model. So whenever we make the sort of assumptions, like here in this case, that the prior has this funky shape or that funky shape, or another assumption or additional assumption is that the neurons are independent. The fact that these are these actually probable lines are not tilted, means that these are independent. Are both assumptions about the sort of natural images and what neurons do, and we can sort of validate these assumptions whether they are true or not, and it will be clear that also Anish referred to one of these earlier, and we will get to this point in a couple of minutes, that this validation is a super important thing. Okay, just very briefly, so we can train this model based on the same on the training objective that I showed before, but I try to be quick with that. So here we have Laplace prior and the likelihood, which is linear, and then without going into the subtleties of the math, what we have here is that the log likelihood is this simple term. This is the exact same thing that Manish showed 2 hours ago. So I don't want to explain. Yeah.
We could study the prior in our brain instead of Yes.
Yes. You can. So it's a really great question. The question is on what level we can do this efficiently. So at behavioral level, the experiment that Mani showed, the ADAS of Weiss and Simoncelli, where you have moving these moving diamonds. I guess it was part of the talk. Then with those behavioral experiments, you can sort of specify some high-level priors that we might have. At this level, like viva neural activations, it's harder. But yeah, so we will see one way to sort of see a justification for the choice of prior that I was advertising here. Okay.
Can I ask you just about? Can we go back about the logic of what you're doing? So X are images, Y's are neural firing.
Yeah.
Before we were thinking of Y's as these latent features from which I can construct images, but now we switched. We're thinking of Y as the neural firing, right?
So we want to make the link that we think that neurons represent the features of the environment.
Okay, but that's a guess or some assumption or something. But let's stick with the Y being neural firing, X being images. Now, if I show X, I can measure Y. Okay, so to write the conditional property of Y given X is potentially something I can measure in a given condition.
Yeah.
Okay. Now, what you're using here is the conditional distribution of X given Y. Okay, which I cannot deduct from the other conditional distribution because what I want to find is Q of X. Okay.
Yeah.
And so because we cannot do that inversion, you're just assuming some form about Q of Y given X. Okay. So first of all, that assumption will be critical, right, for the results.
Yes.
Is that
correct?
Okay.
Yes.
So maybe if you could comment a little bit more on this, like the role of that assumption. But then the second question is the logics. The logics is to say I will make some parametric assumption on that object, and now I will minimize this distance, Leveler divergence, and find the parameters.
Yeah,
that's the logic.
Yes, correct. Yeah, so this parametric assumption you can also refer it to as inductive bias, and as Manish pointed out, up to 2013, where you wanted to do a study with generative models, you were constrained to these linear models. And after that, there came generative adversarial networks and variational autoencoders, which enabled us to go for nonlinear. So what happened before that was that we were just pushing the linear assumption as far as we could, not because we were committed to the idea that the nervous system is linear, but because we only could deal with that. The upside is that the linear thing proved to be effective, as Manish also pointed out, for linear or close to linear models. And then when we have these new developments, when you sort of get rid of these constraints, then it will be again sort of difficult because you need to inject some sort of an inductive bias into your model in order to somehow constrain what sort of representation you will obtain. Hopefully, I will get to that point later.
If I just one more thing about it. Okay, so imagine that Y, I think of it as activity in V1.
Yes.
Okay, which I guess is something that is done. I mean, people have discussed that. Now, X will give you the identity of the image. And in some cases, there are neurons that are downstream from V1. So say that will be much more selective than V1 neuron. So I can think of those neurons as labeling X.
Labeling?
I mean, having a mapping to X.
The higher level neurons.
Phase
Yeah.
selective.
Yeah.
Okay. So the Q of X given Y will be similar to the mapping from V1 to some downstream area, which is much more selective. And that should be much more complicated than the kind of conditional distribution that is generally assumed, like linear mapping plus noise. You see what I mean?
Yeah, so at higher levels, certainly you will not fare well with a linear model.
So then how do you choose it? I guess that's my question.
That's a sort of an open question. So you might have a sort of inductive biases that are there because of the columnar organization of the cortex, which sort of, if I may allude to this terminology, it is similar to the assumption that a convolutional neural network makes, which is translational invariance. So the columnar organization is sort of can be thought of as a proxy of translational invariant representation. And there might be lots of others which we might know from psychology, like the Gestalt principles, which we know help us recognize objects. And recently there were studies that show that if you incorporate these Gestalt principles into neural networks, then it will help learning a lot. So those Gestalt principles, which could be considered as a sort of rule of thumbs for object perception, actually seem to be sort of nice inductive biases to learn. How it is implemented in the brain is one question, but certainly once you want to have more complex features, neurons that are representing higher level features, then a linear generative model will not be good for you.
There was still a clarification question regarding the parameter theta. If it's in your model, if it's A and sigma.
That's right. So theta is a sort of the machine learning general terminology for summarizing all the parameters that you might have, and in a particular linear model that we explore here, we might have just A and lambda as parameters. That's correct. So theta is sort of a general terminology for all the parameters that I might have in my model.
Gergo, there's one or two other questions in the chat. Do you prefer taking them or leaving them for later? I think we can take them.
Yeah,
is it okay?
I'm absolutely happy. Yeah, that's why we are here.
So maybe we could understand the matrix as a decomposition of image text on some primary function, for example, Fourier, which is more likely to be what happens in our brain.
I might need to read this.
By the way, while you read, we get many more questions from Beijing. You guys should feel ashamed about it.
Yeah, that's a great question, and it turns out that if you have a particular prior, like the Gaussian prior, which we had. Sorry, I will have. So I used it as an illustration. When we have a Gaussian prior, then we will actually obtain a decomposition of the image into Fourier components. We will see that in a minute. Like, yeah. So I will skip through this. So here, actually, originally it was meant to be sort of a local project to do this this training. So the original teaser was that in a linear model we might have some sort of we might learn a generative model that can decompose the image into beautiful little objectlets. So formally, we thought of this as somehow linearly combining these vectors into axes. But what we actually have is this. When we have this Laplace prior, these are certainly, when we train the model on natural images, it's certainly not houses and students and clouds and fairies. Instead, we have these little wavelets, which are close to a Fourier decomposition, but what is even closer to the Fourier decomposition is when we have a normal prior. When we have normal prior, it's indeed a Fourier decomposition of the image. And I repeat here that these are result of training on natural images. So these features seem to be sort of the natural ingredients or the natural underlying causes for natural images. Okay, so the answer to the question is yes. When we have a linear model and when we have a Laplace prior, a normal prior, then it's a clear Fourier decomposition. This is called an independent component analysis, and this is then called factor analysis. Okay, and then we might want to cross-check with what's going on in the brain. So we want to check the sensitivities of neurons in the primary visual cortex, and those are more like these things that we see here, these localized oriented filters. Sorry, there is something going on. More like these wavelets than the Fourier components. Okay. And so now we get back to the question that we had before, to this validation issue, whether it is good that we assume this particular form of distributions when we constructed the model. So it goes to also to Ruben's question and the question that came from the right. So we can check that the residual distribution of errors that we cannot account for is similar to the one that we assumed, the normal noise. So here we have a log-log scale, and in the log-log scale, the normal distribution is a parabola, so it nicely matches. So it's sort of reassuring that the residual variance is similar to the one that we assumed. Now we can also like a simple comparison between how the correlations between pixels depend on distance, and this is the empirical distribution, and this is the red is the one that is measured in the Q of X, right? And as for the prior, so here. So there was also this question whether we can identify the prior in any ways. So
those previous two results will depend on the choice of prior for Y, right?
Yeah. So the whole thing depends on so within a particle model you can validate your assumptions. It's not a general one whether the Gaussian noise is good or not. In this part, if you have this particle model and you have these specific assumptions, then you will be able to check whether those assumptions hold. It does not say that the observation noise is normal, full stop.
No, but for example, for the correlation between pixels this correlation function that you got in the print, then did you fit the prior of Y also, or you just wrote down some Gaussian with an arbitrary width and then you just optimized your linear matrix?
Yeah, so the correlations will be is a very, very strong feature of natural images. So one thing that this thing might depend on is the choice of prior, whether how wide this is. But So if you train on large enough number of pixels, of natural images, that will be strong enough to enforce this learning of this pattern in correlations. So it does not really depend on the prior.
So maybe I don't understand what you're doing. I thought you're choosing a prior on Y, then you're optimizing for a Q of Y given X. That will give you a Q of X, which is your variational Q of X. And that's what you're comparing with the empirical P of X, right?
Yes.
So this will depend on the prior you've assumed for your neural activity, Q of Y.
Yes.
Is that correct? Okay, and that prior, is it also fitted or it's not?
No, not really. But so the correlation between the pixels, you would have the same correlation structure if you had a normal prior as if you had the Laplace prior. At that level, it doesn't make a huge difference. So because the main point is that the correlation between the pixels is the second order statistics. The matter should learn the second order statistics no matter what your prior is. So it's not very complicated thing to learn. So it's sort of really a baseline validation. And then one can then check whether the activations of the latents in this model are indeed different from normal. So on natural images, whether it is true that this latent will have an activation distribution that is non-normal, and so we see that. So this is like a pyramid. This is exactly the Laplace distribution. The technicalities is that one can ask how exactly we calculate this. So here's the math. I don't want to go into that detail. So we can do that. So for a large number of images, we calculate these activations, and then from this we can obtain the distribution pretty easily. Now, again, the validation is getting to the point where Manish was at. It's this bow-tie distribution that characterizes the natural images. On his example, it was with Einstein. Right now, these are just two pieces of images which I don't show. This is from the paper of Odelia Schwarzenegger or Simoncelli. So I just want to reiterate from Manish's point that so our assumption was that the prior is this circular thing, or at least it is not tilted in any way. If it is not tilted in any way, it tells us that our assumption is that these are independent. But what we see here is that when we look at the activations of Y and we calculate the distribution of activations of Y2, another filter. So Y1 is one filter and Y2 is another filter. Then we see that there is dependency, and this is bad because this violates our assumption. This is a sort of lesson. So our validation fails when we try to validate the assumption that these are independent. No, they are not. And one mechanistic way to describe this effect is this, that the variance of filter 2 grows as the activation of V1 grows. So the expected variance of Y2 will be larger and larger with the growing activation of Y. So this is sort of a mechanistic description. And again, I want to provide you with a view that directly relates this this discrepancy between the model and the natural images to some updates to the model. So this is what we thought that these are independent, which is obviously not true because they depend on each other. So motivation why this might be the case is this. So if you consider a natural images like this photo of the Pantheon, then we do this photo in a bright sunny day. We have high contrast, and the pixel intensities will have a high variance going from white to black through medium values, right? When we decrease the contrast, then the pixel intensities will be more constrained to the middle ground, so the variance will lower. When we increase or decrease the contrast even more, then the variance of the pixels will decrease, right? And this is exactly what we saw, or it is not exactly, but it alludes to a correspondence between our previous observation that the variance of expected variance of the activation of Y2 depends on how much Y1 is activated, because apparently the contrast and pixel variance depend. It's not a revelation, but it's pretty obvious. Oops. Hopefully I will not do something really bad. Okay, sorry. Okay, oops, I always make this mistake. Okay, so that was our original model. We thought that our images are overlaid little filters, right? Linearly combined little filters. But in fact, even when we do not change the content of an image, the contrast might change. And this contrast scales the pixel intensities, right? So it's sort of a natural ingredient of natural images, because the sun comes and goes. These days, not that much goes, but it stays with us all day. But so if we take it seriously, then contrast is a component that should be represented in our model of natural images, because it is something that scales the variance of the pixels. So if we incorporate the contrast as an independent variable, then our likelihood will be caused instead of this factor analysis or independent components analysis that we had before. Now it is called the Gaussian scale mixtures model, where the only difference is that instead of a purely linear relationship between y and x, we also have the contrast as a multiplier. So now the theta set of now we have an extra variable, latent variable, the contrast, which is not something that we really care about. We do not make inferences about contrast. Mostly we make inferences about the content. Still, it affects our inferences. So the bottom line here is that, which I don't want to go through all these experiments, but the bottom line is this: when we incorporate this natural feature of the natural images, that the contrast might change independent of the content of the images, then we end up with a simple model, which is still pretty linear, the Gaussian scale mixtures, and then it will account for a large spectrum of observations on contrast invariance, cross orientation suppression, and stuff like that in V1. So this is how far we can get with these linear models. So it is time to just recap briefly. So with these deep discriminative models, we had this feed-forward architecture, which was beautifully effective. Here we have, well, at least the promise of a generative model, which is hierarchical. Unfortunately, we're only able so far to address this lower part of the thing. but sort of I motivate you to think of a possible avenue going down on this road that we might want to learn a hierarchical model of natural images in this unsupervised setting, and we can directly contrast the computational goals of this. And right now our problem is that the hierarchical nature and whether it is feed forward or not, whether it is constrained to feed forward or not, has not really been explored. So a couple of questions remain, like whether we can do the nonlinear mapping from Y's to X's, how can we make hierarchy, and whether the information flow is really hierarchical or feed forward. So I don't know whether I still have time or not at all. I guess not.
Well, the official end is in 5 minutes. So if that's a natural breaking point, maybe we can have a couple of questions and then we'll continue in your other lecture. If you prefer to use these 5 minutes for yes.
Let me very briefly check whether there's a natural extension of this talk or not. Sorry. Yeah, so I will use these 5 minutes just to motivate the different sort of open questions, so that those do not remain so abstract. The first one is the nonlinear mapping from Y to X, so having nonlinear generative models. So a beautiful case that was made by Jim DiCarlo is this. So if you have objects that we want to recognize, then there are variables that are so-called nuisance variables like pools or lighting. You want to recognize those images irrespective of the particle pools the images in or the lighting conditions. If you look at the pixel activations, the activation of a particle pixel, then we change the pools and the lighting for these two objects, like this rubber ducky and teddy bear. You will see that the activity of the particle pixel will change like crazy when you move along this direction. You change the pools or change the lighting, which is really bad. And somehow you want to have a representation which is such that when you change these variables, which I will refer to as nuisance variables, the activations will not change. So you want to have a representation which is such that it becomes disentangled. So when we change lighting and pools, we can safely learn a decoder. Then we can safely decode it from any pools that we might have. And clearly, in order to get from this funky sheet to this less funky surface, you need to have a nonlinear transformation. And we are looking for this nonlinear transformation. The nonlinear transformation sounds like super abstract thing, and it's not really approachable. So let me just show you that some really humble components of neural networks can contribute to this untangling, this representational untangling. So it turns out that even if we have just grating stimuli, we have similar situation that when the gratings are moving, then it is hard to get a decoder that would linearly separate the two orientations. And so it turns out that the only nonlinearity we actually need is nothing else but this super humble threshold nonlinearity. This threshold nonlinearity, the threshold linear value, rectified linear unit kind of nonlinearity. This is the core, or this is pretty much the heart of all the artificial neural networks that we use today. And an intuition why it works is this. When we have this firing threshold, then we can move our neuron to transfer information with more fidelity. So if we move the threshold upwards, then obviously we clip all the activations, and the activity of the neuron will be non-informative, completely uninformative. If you move it down, then all the information gets through. So it sort of suggests that it is a good idea to move the threshold down. But there is another direction or other to this, which is that if we move the threshold to the other direction, then we will increase the sparseness of the activation of the neuron. And sparseness, well, it is not. Sparseness is in an intimate but sort of tangible relationship between representation and untangling. So when you have a less sparse representation, or sorry, a more sparse representation, then the decoding of the linear decodability of your code will be more probable. So apparently there is this trade-off between increased information transfer and increased sparseness, which can compete against each other. And so if we just multiply these two competing forces, then we have an optimal window where the threshold should be. And this is something that we can check on data, whether it is true. And it turns out that V1 neurons are actually tuned such that this regime of robust representation untangling is co-occurring with the regime where the firing threshold of neurons is. Yeah. So and nonlinearity is obviously present in the features that higher level visual cortices represent, like neurons in the V2 are representing or sensitive to textures, and this motivates the use of more nonlinear models, which will then go after and during my next talk. Okay, thank you.
Thanks a lot.
Now we can move on to the license side, so you can stay there, and maybe Manish, you can come and maybe.
Yeah.
I think that's good. Yeah. So I leave it to Stella to moderate it. Yeah, sure.